Okay, so good evening, everyone. How's the week going? The 5 hours or whatever. No, hang on. The morning session. So is everybody energetic for the rest of the week?
Yes.
Okay. I think some of you are finishing up with 570, right? Is this the last week? Okay. Good. Um, so if you want feedback on assignments, try to get in touch with the TA if he has not commented, through the Blackboard system on if you have lost points. Okay. Um, so let me jump into today's material actually directly. Yeah. Any questions? Yeah. Is there? Some people have.
Not yet. Not yet.
Okay, so it's in process. So okay, for that definitely don't contact EA. He's doing it. He will get in touch. He will update it as soon as he gets through. Okay. So actually, there's a part left from last lecture. So maybe in the next 10-15 minutes, I'll cover that, and then we'll come to today's goal. So maybe, actually, let me jump directly into that. And also, I think last time there was a clarification. So how many of you went through the posted handwritten notes from last week? Nobody? Like you should eke out at least a minute or 5 minutes out of whatever 168 hours to look at the notes, because last time I think we were trying to show the relation between the lasso, the least squares objective with a penalty or whatever regression it's called, regularization term, right, which was an L2 norm square actually. And we tried to show that it was equivalent to a constrained version where the constraint was with respect to the betas being less than beta transpose beta less than some tau, right? So in the notes that I posted last time, actually maybe I should just open it. Um, okay. So there's a part which is missing why, having that constrained version is the same as the original problem. Okay. So the original problem had some solution, beta star lambda. Okay. So where lambda is that trade-off parameter which was balancing the least squares of loss objective on the data and the preference over small norm beta coefficients or small norm models. So we showed that, first, I think if you show that beta star is also a solution for the second problem, you need to show that it is first of all feasible. It is feasible just because, beta star to use, left hand side is exactly equal to right hand side for this choice of tau. So it is feasible. Now we have to show that for any other beta, the objective of the second problem is, okay, there's a bracket missing here, but some square loss. Sorry, we're not showing that beta star is. Now we are showing that beta star lambda is also the minimizer for the objective of the second version of the problem. Remember, second version of the problem only had least square loss. Right? It was just a minimized least squares loss subject to some constraint. We said the constraint at least is, remember the constraint at least is feasible that we saw last time. We also did some geometric stuff, but what we need to now show, I guess these two lines basically with some explanation below, is trying to show that beta star of lambda is also the minimizer of the objective of the second version of the problem. Second version of the problem has an objective which is only this, okay, right, least squares loss. But we only know something about beta star lambda, which is that beta star lambda satisfies the first objective, minimizer of the first objective, which is that it's for any other beta, this, when you substitute beta star lambda, is smaller than that other beta, whatever beta that is, okay, smaller than or equal to. So now you can just push this guy to the right hand side. Okay. So the square loss, which is the objective of the second term. Maybe I should use this. Anyway, square loss for the objective of this of the second problem is less than or equal to the objective of the first problem plus some. I mean, the term that I pushed to the right hand side. But you can see that beta 2 norm of beta square minus 2 norm of beta star lambda, that 2 norm square, that difference is actually less than or equal to 0. Okay. Why is that? Because of the constraint in the second problem. Okay. So that means this term is going to be less than 0 as long as lambda is positive, and we assume lambda is positive. Okay. We want to trade off two things, right? How well is beta fitting the data, and how well is beta small enough in terms of the 2 norm square. Okay. So anyway, this if you don't want the intuition is just this is true because of the problem's constraint. So this term is negative, which means that if you drop this term, I mean, if left hand side is smaller than right hand side plus a negative term, then you can drop the negative term without any issues, and therefore you have the beta star lambda's value in terms of the second problem's objective is less than the objective value for the second problem for any other beta. Okay. And so we showed that beta star lambda, which is the solution of the first problem, is the solution for the second problem. Okay. What's the connection? Why is it the connection is that we chose the tau in the constraint to be exactly beta star lambda 2 norm square. Okay. So for this, you want to kind of look at last time's notes. You don't have to rewrite all the stuff. You just go back to where we were talking about. Where were, yeah, we were talking about this problem and this problem. Have a look at this slide, and there was some geometric intuition that I was showing in the next slide. But we need to show a little bit more, and that was the red part on the last slide. Okay, but I don't want to talk about ridge regression more. I want to spend some time on lasso. Okay, so it's actually maybe even before lasso. Let me just quickly recap. This is again not related to lasso itself, but this is something to do with principal components. So last time it was towards the end of the class, and I threw in a lot of terminology, right? How many of you agree with that? Okay. So there's something called principal component regression. Okay, it's just a slight variation of the problem. Just like in subset selection, if we had 10 variables, I said 10 input variables trying to predict something like an output. Okay, so instead of the 10 input variables, you could in subset selection you would drop, let's say, 5 of them, and maybe you will only use 5 actually relevant ones. Let's say. So principal component regression is also has a similar flavor. It's trying to first pick up some principal components, and I'll tell you what principal components are. Intuition wise, they're just some arbitrary linear combinations of input features. Okay, so principal components are nothing but some combinations, linear combinations of the input features, by which I mean I'm only thinking in terms of the data matrix, because we are trying to build actually a model. So this is a data matrix, which is n cross p, right? So remember subset selection, we try to drop some columns here. It essentially means setting the beta hat for that coordinate to be that feature to be 0, right? So in principal component regression, we are just trying to come up with some principal components, which I will literally write it as d1 times u1, d2 times u2, and so on. Okay, this is also going to be n times p. Okay, there will be these are called principal components. I'll tell you what u's are and d's are pretty soon. Okay, so actually u's and d's are nothing but n times p, d p times p, and then v transpose. This is p times v. Okay, so this is the decomposition matrix, singular value decomposition of the data matrix, right? These are called principal components. Okay, so these are just the same dimension. U, for example, has columns which are n dimensional, right? N length vectors. So principal components are just, but intuition wise, what is this? This is nothing but some sort of a linear combination of some features of the input. So for example, you can think of, just as intuition, you can think of U1 as like, half of the first column of first feature plus 2 times the second feature. For example, that's some combination of, I didn't take all the, let's say P is 10 for example. Instead of taking all the 10 features, these are columns, think of these as n-dimensional columns. instead of taking a linear combination of all of them, I just said, let's say u1 is just 1/2 times the first guy plus 2 times the second guy. Okay, that's u1. Okay, or d times d is just a scalar. Okay, d1, d2 are just the entries of the diagonal entry, so they're just some scaling things. So that's it. So these are called principal components. Okay, these vectors are, you can think of them as new feature vectors. Essentially, that's all it is. And then you're saying, okay, maybe I can take the top 3 principal components and just do regression as before. Okay, that's principal component regression. So what does it mean to pick the top 3 principal components? Is in terms of like the variance, right? We saw that there is actually um, yeah. I was just saying that. So what's the best way to say this? I think last time, I'm just trying to recollect. Last time, I think we derived the data matrix times the first vector. So the first vector in this V matrix. So the V matrix has p vectors, which are p-dimensional, right? Think of if it's V transpose, then you just transpose those vectors. But anyway, if V transpose has vectors like this, actually v1, v2, v3. Okay, I guess row vectors. So that let me put transposes there. So this would be V transpose. Okay, where this is p cross p, right? Which means there will be p rows or p columns, right? So I'm just saying that think of the first row. That vector is this v1. Okay, so that v1 is called the principal component direction. Okay. V1 is called the first principal component direction. Vp is called the pth principal component direction. These are just directions. These are p-dimensional vectors. And x times v1 is actually equal to d1 times u1. Okay. This is a fact. I think maybe we'll revisit this when we talk about principal component analysis. Few lectures from now, six lectures from now. But for now, all I'm trying to say is that principal component regression, in terms of intuition, that's the most important thing I'm trying to take away for the next, for 2 minutes here, is that you had the original data matrix. It's like you're trying to create new columns. Each column is some sort of a linear combination of each of the original columns in my data matrix. That's what these are. Okay. I mean, how do you see that? You can just see that by the column space of x and column space of u have to be the same. Okay. You can kind of merge these two together, and or you can d you can ignore because d is just some sort of weight on each column. Okay, so that's what these are. Okay. You can actually drop v and say d times u1 first column, d2 times u2 second column, and so on. So it's just a u times v transpose matrix, and you can actually see that you're just doing some sort of changing the data matrix into some sort of a linear combination of these vectors instead. Okay. So I guess the more succinct way to say this is you're just changing the basis. So look at the refresher course for linear algebra to understand what is the change of basis. So all we're trying to do is that original data had the usual coordinates, first feature coordinate, second feature coordinate. In the new, all we're trying to do is to change the basis by using these V's. Okay, V's are eigenvectors, or sorry, V's are principal component directions. Okay, they're going to be orthogonal to each other. So it's as if the data was transformed into looking in terms of these new coordinates, and the magnitude of each new coordinate is going to be the first component here, and so on. Okay. That's the idea. It's just a change of basis of the original data. Now you can drop some dimensions because of some what is it called variance or variance capture idea, but that's principal component regression. Okay. So first, just to SVD in terms of operationally, just to SVD. Okay, pick up some components like first 3 components, and then just do regression. Okay, you have 3 components, which means that you have 3 new feature vectors now. New 3 features. So you just do a 3-dimensional regression, for example. Okay. Any questions about this?
This is a step. It happens always that you pick the 3 first components.
No. I just suggested 3. Yeah. I mean, how do you choose the 3 and all that is again choices, just like k nearest neighbor. So there is some art there.
Also,
not art, but like you can do cross validation stuff like that.
Also, how do you choose the basis? That's like it. What is the
No, you're not getting to choose the basis. Basis is gonna be just output when you do SVD of this matrix. There is no. It's a unique. Unique up to some rotations and so on. Okay. So these are. I think last time I was talking about orthonormal. The columns are orthonormal and orthogonal, and columns here are orthonormal. Okay. Columns. The B's are orthonormal. Orthonormal just means like inner product is V1 is orthogonal to. Orthogonal just means that V1 is orthogonal to V2, which is inner product of V1 times V2 is 0. Okay. So these ideas just go back to the refresher. I think I explained there clearly than in the 1 minute pitch I'm doing there. But all I'm saying is you don't get to choose the basis. Okay. These are principal common directions. You just do SVD, you'll get them. Okay. And use also you just do SVD, you'll get them. D also the same. You just call these principal components, and you pick some of them only because I think last time I mentioned that these are ordered in terms of their decreasing magnitude. So D1 has the highest magnitude. So picking 3 just means capturing the highest amount of variance. And there was a picture last time, right? We're gonna discuss this again in the context of principal component analysis. Yeah, principal component analysis. So we'll revisit at that time. Yeah.
So, for example, as you said, if we choose 3 components,
yeah,
and this would be sorted across, right? So,
yeah, let's assume we are sorted. If it's not sorted, you sort it. Yeah.
So, assuming we are taking 3 components, we'll take U1, U2, U3, right?
Yeah, with the multipliers D1 and D2. I mean, you don't need the multipliers essentially because again you'll get the coefficient. I mean, ultimately, if you're building a linear model, you'll anyway get some coefficients as you scale it up. Anyway, that's principal common regression. Actually, I think you should retain them. Let me not deviate from that. So now we're going to look at lasso. So it has a full form, right? It's an abbreviation for least absolute shrinkage and selection operator. But there's a lot of history about lasso, and I think it's even actively investigated. In high dimensions when number of features is as many as the number of labels and so on. Sorry, as many as the number of observations and so on. But for us, we'll just try to kind of understand it in the context of ridge regression and subset selection. Remember, the whole point of doing ridge and lasso was saying that subset selection is too discrete. It either completely eliminates a feature or just keeps it. Okay. So we wanted to do a softer control, like maybe part of the features are not exactly like keep and remove, but maybe a part of the feature is kind of useful for prediction. Okay. So I mean, less weight on the feature and still it's useful for prediction. That's what we wanted to get to. And lasso has the same form, almost the same form as ridge. So it's just y. So I'm just writing the least squares loss. So this is a vectorized notation. We have been seeing this for the past 4 lectures. So plus a lambda. I'll use this notation. Okay. So norms are just properties. I mean, they just map from a vector to a number. They have some nice properties, but for us, we just think in terms of regularization. So this is essentially equal to sum over j is equal to 1 to p of beta j absolute values. Okay. And it's called an L1 penalty. So why are we calling it a penalty? Because we're minimizing these things, right? The first term is the usual least square loss. We're minimizing it. The second term is a preference, a regularization preference that we are adding it. Preference as a bias, it's all the same thing. Okay. So remember, in the larger scheme of things, we are biasing linear models further, right? So it's called L1 penalty, because it's called, this norm is called the L1 norm. Okay. Generally, it's written as L1 norm. So it has almost the same form as ridge regression, except the norm has changed here. And so unlike ridge regression, there's no closed form expression, analytical formula for beta hat. Okay, beta hat ridge had it was just some lambda I additional term coming into your matrix inverse type of a formula, right? So here there's not going to be any such thing. So you'll have to use some sort of iterative procedure. And we have seen, I think we have at least, I guess, very briefly discussed gradient descent. So this is a problem. You want to find beta. Beta is a vector. You want to minimize this objective while trying to find the best beta, which has the lowest total score here. So you can try to do variations of gradient descent to, for example, minimize this. Okay, there is some issue with the gradients with this norm thing, but that's a operational detail. Okay, for us for now. So key point: it has to be numerically computed. Okay. So for both ridge regression and lasso, there is maximum likelihood estimation interpretation of both these penalties or regularization terms. But when I talk about maximum likelihood estimation in the next class, I will discuss MLE for these two. Okay, I don't want to introduce. We have seen a likelihood example last time, which was a single one variable random, one variable problem, which was just Gaussian with unknown mean, and we figured out that mean was just the average of the points that we had, right? So the same idea, but we'll apply it to ridge regression and lasso next class when we talk about MLE in its full, I guess, a little bit more generality. Okay. But today, I think with lasso, I only want to say one thing, which is I'm going to contrast it with ridge regression. Before that, as I said, you have to numerically solve for beta hat, and it turns out that this problem is convex. Okay, so convex means remember. So I don't want to write the formal definition; it's just too much notation. So convex just means it's a nice objective function where there's only like there's no ups and downs. Okay. So remember, if you think of least squares problem, it's in one dimension, for example, it's just a parabola type of objective function. Okay. Okay. So if you're literally solving, this is just an example. You're just solving y is equal to mx. Okay, where m is the slope. It's a one-dimensional problem. Then as a function of m, okay, m is the thing that we need to learn. As a function of m, you would have like if you do y minus mx the whole square, you can see that y and x are not variables here. Just think of with some summation here, let's say. Okay, m is not the so y's and x's are not variables. M is the thing which is variable. You'll see that you'll have a parabola, okay, like this, okay, which will be above. I mean, it's a loss function, so it has to be above 0, and you want to get to the bottom. It turns out that we solved for a setting. We found the gradient. We set it equal to 0. We got the closed form expression before, but even this function, you can see that this is going to be the parabolic part anyway, and norms are also convex, by definition. Now you can also show that they have some nice property, convexity property. So you will also, if you do gradient descent or something similar, iterative procedure, you will typically end up at the bottom of the value. Okay. Any questions? This part. So
Gradient descent we have not studied so far, not formally.
we saw gradient descent. There was a R script I gave you in the first lecture itself, isn't it? I mean, if you don't want to look at the formula, there was a R script that I already gave you, right? Which was doing linear regression, and we saw. Did you run the R script? Did anybody run the R script? No. Okay. Anybody run the R script? You should run it because it shows both the LM. I think probably some of you have used LM. Is it? You've used LM. So the R script is, if you don't know LM, if you don't want to use any packages, because some packages, by the way, you cannot randomly use it if you're in a company if it's not licensed appropriately. Okay, so you will get into trouble. But anyway, for these simple problems, anyway, you can just do gradient descent. And there was a gradient descent code. I think some people even asked me questions about what's happening in the in the for loop. It is an example of a for loop in R as well as an example of doing gradient descent in R. Okay, so have a look at it. Both of them give you the same answer. Okay, LM function and the gradient descent example. That's just one example we saw. Okay, so now I want to quickly contrast ridge with lasso. Okay, so we actually, so this is just a illustrative diagram. Okay, two-dimensional problem, beta 1, beta 2. I said there's a beta hat here. Let's say beta hat as in a beta hat least squares. Okay, let me just put that as without the penalty terms. Okay, and remember, so this is supposed to be at the bottom of the valley. So bottom, since it's a parabolic function, this least squares loss, we'll just look at contour plot. Okay, this is a plot that you'll see when you look at maps. If you go hiking, you'll see such contour plots. Okay, so anyway, what is a contour plot? So let's say just draw it some way. Okay. So these are I'm trying to draw the same diagram. Okay. It's messed up, but so what I want to show is that the ridge penalty we saw is like a ball, right? So I mean, in fact, it's a circle with the inside part being the valid region when it's in 2 dimensions, right? Remember, beta transpose beta less than or equal to some threshold, tau. Tau is a Greek symbol. And so this we saw, it was just beta 1 square plus beta 2 square less than or equal to something, let's say 1. Tau, let's say, is 1. Okay. So that's the definition. That's the area covered by a circle, right? Now this guy, 1 norm, is going to be something like this. Okay. So this is let's say 1. So what are these points? 1, 0, 0, minus 1, and similarly. Okay. So they are just geometrically different. And okay, in 2 dimensions, you may say, oh, it's almost the same. I guess it's not figuratively too different. But in higher dimensions, there is going to be a consequence. Actually, a little bit of higher dimensions beyond 3, which is what we cannot visualize. And so, okay, why this picture is to show that sometimes you, with this guy, with lasso, you will actually get sparse solutions. Okay, which is akin to saying that there will be some betas for which it will be the values will be 0. Okay, and the idea is that when you have this, so what is our optimization problem? If the area restriction was not there, like this or that, then the whole beta region is valid, and then you would just get beta hat least squares, right? That was the original problem. But if there is an area restriction, then you want to balance. Oh, I want to keep a beta inside here, but it has to be also close in terms of the bottom of the valley, right? There are 2 objectives, right? And so, what would be a point inside here which will be close to that? Maybe a point on this horizontal. I mean, this is the face, or it could be this point or this point. Okay. But here for this we actually saw that there was the solution will be on the boundary. If it is like this, if beta hat is outside, the solution will be on the boundary, and it will be somewhere over here, right? Which will be the one which is still valid, which is inside this region, but it is also closest to this point, right? Geometrically. So anyway, with the second, with this, it turns out that in recently, even in 10 dimensions or beyond, the chances of these corner points or the face points hitting the being the optimal is pretty high. Okay. So an extreme view of that is if I just increment this contour plot, maybe this is the point which is the solution. Okay, this is just for illustration purposes. This will not be the solution. It could be also over here. But this kind of captures sparsity. I'm trying to relate it to subset selection where some of the coordinates are exactly set to 0. Lasso will inherently, although it's a convex objective, you're just doing some gradient descent, and we are not explicitly talking about subset selection at all, except for the choice of the lambda parameter. We will still get solutions where some of the coordinates will be 0. Okay. And actually, there's a picture. I think last time. Just close this guy. I think last time we saw this one where we just said if lambda is really large, all the beta coefficients will be zero. So that's what these coefficients are, and as lambda is shrinking close to zero, then these are the beta coefficients. Okay, this is what we saw last time, and I just want to contrast that with another picture, the second one, which is this. Okay, here again when lambda is almost zero, essentially zero, then this is the same solution as before. Okay, and when lambda is now increasing in strength, you will see that some betas are already set to zero. Okay, some coordinates are already set to zero. And this is basically saying everything will be set to zero. Like in this between, if lambda is large enough, then there's only one guy which will be like non-zero, this LCA volume or whatever, and everything else will be set to zero. Okay, so there's some sort of a soft control on the which features are to be included for prediction. Okay, so it depends on your preference as well, and the lambda how will you choose based on cross validation. Is that clear? Um, any questions?
Can you repeat sparse solutions? What does that
These are sparse. Sparse just means many of the beta coefficients are going to be zero. Let's say in this region, for example, 1, 2, 3, 4, 5. 5 of the beta coefficients are zero. So and 3 are non-zero. So you can think of that as a 3 sparse solution if you want. Sparse just means very few, right? Very few being non-zero. Okay. So for those of you who want to intuit from here, just think of it as like this is a turned square, but in high dimensions you can think of it like a diamond. Okay, in for example 3 dimensions, instead of a square you would have a diamond shaped region. Okay, and so this contour area hitting the diamond on the face, not on the surface but on the edge, is higher. Okay, on the edge, one of the coordinates will definitely be zero, right? So in higher and higher dimensions, the contour, these contour lines touching an edge of that diamond thing is going to be higher, and on the edges of the diamond are I guess subspaces basically. Some of the coordinates will be zero. Okay? That's what's happening. Any questions? Yes.
So how does that capture more data points like in a non-parametric way? Where
We are not capturing more data points. This is not in the data space at all. This is in the parameter space, two-dimensional problem.
method, yeah, I'm saying how do you capture more of that diamond? I'm just trying to
Think of a three-dimensional problem. Three-dimensional problem. The lasso penalty looks like a diamond-shaped preference where you only want the parameters to be inside the diamond. Okay, but it turns out when you solve the problem, because you want to balance both being inside the diamond and the contour surface, that's basically going to be a point on the intersection of the contour surface. One of the contours which is closest to the bottom of the valley and the diamond, and that need not be just the corner of the diamond. Okay, for example, in 3 dimensions, how many corner points are going to be there? 1, 2, 3, 4, and 5 and 6. Okay, in z-axis, six corner points. But those are not the only points you need to touch. You can also touch the edge. Okay, on the edge also you will get one of the coordinates to be zero. That's what in 3 dimensions. That's what you can imagine. Higher dimensions, a similar thing happens. Is what I'm claiming. Okay. Yeah.
Can you conclude that lasso is better than the ridge because it reduces the subselection as well as it reduces the coefficient to zero also?
I don't know if one is better than the other. So we have to qualify what is meant by better. We have not. So we have one though. We have one way to qualify, which is EPE and stuff. So these are just preferences. Okay, these are just softer variations of subset selection. But those preferences may not be true. So you're trying to balance your preference, which is this regularization term, with the fit with the data, which is the least squares term. Okay, that's how you're biasing, right? Otherwise, if you don't care about preferences, then you just do least squares, given that we are in the linear modeling setup. So it's not clear whether your preference is the actual, is related to the true data generation process and so on. So I'm not saying one is better than the other. That has to be left for EP and cross validation, something like that. But if you care about sparse solutions, maybe you want to use lasso if you don't want to do subset selection. Sparse as in like some of the coefficients. You want to drop some of the features, then lasso will let you do that. Okay, so now let's go to next. The actual content of this lecture. So today we'll look at, I think probably the last lecture talking about linear models, except for maybe SVMs later. So these are the goals for today's lecture. Classification. Okay, so far we've actually ignored classification, except for maybe in the second lecture we talked about Bayes classifier. Okay, we'll kind of revisit that topic. So classification is a very important problem. In fact, most recent hype with computer vision, image classification tasks are the prototypical tasks where you show really good performance. Even in your assignment, you're using the zip code data set. It's a classification of digits, right? Those are actually images, but you're vectorizing them into some 700 dimensional vector, 784 or whatever, right? So those are classification problems. So you're doing two-class classification. You can also do more classes. So first thing, if you know regression, and we spend so much time on regression, if you know regression, you can always do classification, even if you don't know any other classification problems, classification method. Okay, so we'll see first how to use what technique we know, regression, in fact linear regression, to solve classification problems, and we'll point out a couple of potential issues that it can have, and therefore we'll talk about how to get how to use the next simplest model classes. Okay, one of them is called linear discriminant analysis. The second one is called logistic regression. And what's interesting about all three techniques? Okay, one is just by regression. So far, whatever we have seen. Second one is LDA. Third one is logistic regression. The common point is going to be they'll give us linear decision boundaries. Okay, that's why these are called linear classifiers. We'll recall what is meant by decision boundary again. And then we'll kind of finish off with some quick discussion on cross-validation. Okay, some nuance on cross-validation. We introduced cross-validation 2 lectures ago, but we'll revisit. When maybe it can fail. Okay, because of the choice of your number of folds or things like that. Okay. Any questions about today's goals? So at the end of the day, you want to understand how to do classification at least 3 ways, and maybe a little bit about shortcomings or what things you need to take into account while doing cross validation. Any questions with the goals? So if not, let's directly go. Okay. So first one, using regression for classification, linear regression. And so now our variables are slightly different. Now we're going to use x comma g, right? G is our qualitative variable, and so g takes, let's say, k values. Okay, we'll probably not visit knn, so don't worry about the k from knn. So g takes k values 1 to all the way to k. Okay, capital K, let's say. Those are k classes: cat, dog, fox, something like that. And the objective of classification is to actually just divide the input region into parts, right? Parts where one of the class is true are the highest in terms of its likelihood or probability, and parts where some other class is the highest in terms of likelihood. Okay, we saw this orange versus blue two-class classification problem. So we had somehow we could partition the space such that there were 2 regions, right? It doesn't have to be 2 regions; it could be more for even two-class classification. So since we know linear regression, so one way to use regression for classification is as follows. It's a very simple idea. Okay, so if you have k classes, then create k variables, y1 to yk. Okay, output variables. Now these are output variables where these are just one hot encoding of the class. Okay, of the output qualitative variable, which just means that y1 is going to be 1. For example, let's say, let me put a tag at the top. So let's say the g, I can't put tag for this. But okay, let's say G was class 1, class 2, class 1, class 3, 2, and things like that. Then let's say in your data, okay, there's n cross 1 here, okay. So I'm not representing G. Let's call it G, I guess, data. Okay, I'm not putting a tag at the top because it's not clear. So this is that output variable in this classification problem. Instead of this, you would just do the one hot encoding, which would be just ones, all zeros, right? 0, 1, all zeros, and 1, all zeros, 0, 0, 1, all zeros. So this is one hot encoding. Okay, this is fine, right? Everybody is familiar with this. Okay, once you do this one hot encoding, you just regress x on y1, regress x on y2, regress x on y3, and so on. Okay, so you have k regression problems. You just solve k regression problems. So let's call the regression outputs. I mean, so the models to be beta hat k times x. Okay, so for the kth class. Okay, this is little k. Okay, maybe I should. This is a tag here. All I'm saying is for each class, the capital K classes, let's say 3 classes, you're just going to create 3 regression models, 3 regression vectors. Okay, and is that fine? You just have zeros and ones. These are quantitative. I mean, some numbers, and so you can regress. And then what's going to be the addition boundary? Addition boundary is going to be where your two predictions are going to be having the same score, right? So, for example, addition boundary could be where beta hat k x. Again, I should put a transpose is equal to beta hat transpose. I guess let's say L x. Okay, where k and L, think of it as 1 and 2, for example. Okay, so the addition boundary between the first class and the second class is going to be those x's for which the left hand side is equal to the right hand side. In this case, two linear I guess functions of x. So this whole thing is a linear function of x, right? I mean, this whole thing is a linear equation, is what I want to say. Everybody agrees? So this is actually an equation of what is called a hyperplane. Okay, just a terminology. I mean, in one dimension is the equation of a line, in 2 dimensions is the equation of some plane, and so generally hyperplane. Okay, and so the decision boundary is linear because the equation of a hyperplane. Okay, it's like in one dimension you just think of it as a line, right? So we already saw this. If you have let's say class 1s and let's say class 2s and class 3s here. Okay, so the decision boundary would be between 1s and 2s would be a line in this 2D space. Okay, in 1D space it's going to be a point decision boundary. And in higher dimensions, it's going to be a hyperplane. It's a plane which, like in 3 dimensions, you can imagine 2 sets of classes, 2 bunches of points, and then like a plane between them, right? That's addition boundary. Okay, and of course there could be something between 1 and 2, something between 2 and 3. Okay, right? Whichever is the highest 2 scores, you just want to equate them essentially. If it's a 3-class classification problem. So this is how you do classification using regression. But you would say, okay, maybe I'm being too conservative here. Being linear is too restrictive. It's not the case, right? We've already seen this before. You can always transform your input raw features into all sorts of functions of all sorts of functions like squares, cubes, and so on. And then you would have actually a decision boundary which is going to be nonlinear, okay, in the original space. So it's going to be linear in some modified transform space, because in the transform space there will be some linear coefficients. But if you collapse it back and look at the decision boundary, it could be curved or it could be wiggly. Okay. By the way, these are called discriminant functions. I mean, we'll see this name. I mean, not just for linear regression based classification method, we'll see discriminant functions even in LDA and logistic regression. Okay, they just mean things which can discriminate from one class to the other. Okay, which let us discriminate between one class to the other. Okay, and actually, this regression last time I think I mentioned it briefly. So you can actually do this capital K regressions in one go. Okay, if you're just doing least squares regression, no penalties and all that, then I think I wrote this formula. Beta hat is, I mean, we've seen this formula several times now, right? So this can be n cross capital K, and so beta is going to be the same y's that I drew in the previous slide. Okay, this is just the n-dimensional vector, column vector, one for one, each one hot encoded class. You can actually get the beta hat, all the betas for the k classes in one swoop. Okay, so it's like some sort of parallelization going on. Okay, you want to see. So your homework is to understand why this is the case. Why don't I, why doesn't the regression for one get influenced by the other one? Okay, could be in the exam. Okay, so this is good. So let me connect also to one more thing where we saw that we had this best. So first of all, we know that what is the best regression function if we have a joint distribution between x and let's say one-dimensional output y. Okay, we know that the best regression function is conditional expectation of x. Conditional expectation of y given x is equal to x, right? Let's say the best prediction you could have if you had the joint probability between x and y, right? And that's what, so linear regression assumes that this is actually equal to beta transpose x for some beta, right? That's what I mean in this case. Let's put a little x here. Okay. Whereas for classification, the best classifier is actually probability of g is equal to some class, let's say little k, given x is equal to x, right? If we know the joint distribution between g and x. Okay, I mean, in fact, it's actually the max argmax. Let me know. We can take the max. Okay. Okay. What I wanted to say was that if you're doing regression, the best regression function is this, which linear regression assumes to be linear, and actually for 0, 1 valued y variable, output variable, that expectation is actually the probability of y is equal to 1. Okay. Let me actually. Okay. It's equal to probability of y is equal to, I guess, yk is equal to 1 given x is equal to x. Okay. These two are the same. Okay. Because expectation is just y is equal to 1 times the probability that y is equal to 1 plus y is equal to 0 times probability of y is equal to 0. So the second term goes away. So this expectation is nothing but this probability, right? Okay, I should put that in the exam as well. So this, but this probability of yk is equal to 1 is exactly equal to the thing in the center, which is probability of g is equal to k given x is equal to x, right? Because when yk is 1, all other coordinates should be 0, which is the g is equal to that little k class, right? So, okay, where am I trying to go here? All I'm trying to say is that linear regression, if you use linear regression for classification, you are assuming that this is the probably the class given the feature is linear in the feature. Okay. So first of all, probabilities are supposed to be numbers between 0 and 1. But if you think that this is always going to produce numbers between 0 to 1, then we are saying that the probability of the class given the feature, class k given the feature, is a linear function of the feature. Okay, that's the assumption being made when you use regression for classification. Okay, the two issues with this. Issue 1. First of all, beta hat, let's say kth chi, transpose x. How can we make sure that it belongs to, let's say, 0 and 1, right? By the way, this E type of thing is just belongs to short form. You can write belongs to there. But anyway, issue one is that we have a linear function here. If x's are taking some values, maybe betas are such that I'm getting a value, getting a number which is less than one. Oh, sorry, greater than one. Or it could also be that the number is less than zero. Okay, probabilities cannot be less than zero. Right? There's some issue like that. And the second issue is a really nice issue to talk about, which is the idea of class masking. Okay. Okay. Anytime my handwriting is too bad, then just let me know. Okay. As long as it's acceptable, it's okay. So second issue is class masking, and that's what I'm going to spend a couple of minutes on. Okay. So these are just issues I'm pointing out for trying to do classification with regression. Therefore, we'll move to some other techniques which are at least don't have these two issues. Okay, which are linear discriminant analysis and logical regression. By the way, all these are simple methods. It's not like you will use only these methods in your workflows, but kind of really understanding the details of these methods is kind of is a good exercise. Okay, that's what we're doing in this course. So what is class masking? So for that, I'm gonna think of a 3-class problem. Okay. So this is my 3-class problem in 1 dimension. Okay. What could it be? Let's say this is the only feature x1, and I have 3 classes. Okay. I'm gonna say, okay, let's say in fact x1 is between 2 minus 2, and this is 6, and this is minus 6. Okay, some range. Okay, x is between minus 6 and 6. That's what I want to say. Okay, x can only be there, and between minus 6 to minus 2, it's class 1. Minus 2 to plus 2, it's class 2, and 2 to 6, it's class 3. Okay, so basically, if you want like illustrations, circles here, crosses here, and triangles here. Okay, in the sense of like why different symbols, 3 different classes. Okay, so now think of the first class, the circles class. Okay, how does the training data look like? Training data would be just the circles. Actually, training data will not be just the circles. Circles, and training data is going to be all these points, except the y1 will be 1 over for these points and 0 for all these points. Right? It's just an n-length data set where just the y1 the coordinates will be 1 for only the points on between -6 to -2, right? So, or in other words, if you look at the data, it will be something, okay, I don't want to put crosses there. Some data points with ones, okay? It's just y versus x1. That's it. I mean, it's a one-dimensional problem. So it'll be something like this, okay? Where there'll be zeros here. Okay. So if you fit a line, it should look like this, right? In 1 dimensions. It's something going through, at these you have to predict low, and here you have to predict high. What can you do? You want to kind of minimize the least squares, you would probably put a line there, right? So, I mean, let's say the line looks like, I don't know what the best, okay, let's say the line looks like this. Okay, this is just an illustration, doesn't have to pass through that 2 thing and so on. And similarly, the line for third class would be symmetrically the opposite, right? I mean, symmetrically, like the opposite would be something like this, right? For the third class, this is y3. So it's like beta hat 3, beta hat 1, and there also has to be beta hat 2. Now, at beta hat 2, the problem is which way should it slope, right? So I can't slope the left side or I can't slope the right side because the data set is going to be top, ones here and then zeros here, right? So it'll probably be something like it could be here, or it could be below. Okay. Anyway, I mean, I don't know where levels are. Let's say pick two choices. It could be above this crossing or below this crossing, just to kind of illustrate the point. If it's So okay, and now how are you going to classify? So I didn't probably tell you how are we going to classify with regression. So the way we classify is whatever beta hat one times our classification model is what beta hat k transpose x max argmax over k is equal to 1 to capital K, right? It's just a maximum score. Whichever regression produces the highest score, that's the class. That's the most intuitive thing you can do. So you can see that if you know if the line if the dash if the third class or the second class in this case x's class is produces that horizontal line, basically the slope is 0 here, then we can get okay our prediction is going to be this is one class, this is one class, and this is one class, right? Because what are these lines essentially? This is my prediction. This is higher than this dash, higher than this guy. So clearly my prediction here is going to be this class. No estimate, most intuitive thing, right? Here you can see that the score for the dash line, the beta hat 2, for example, is higher than the score for using beta hat 1 and 3. So my class is 2. So here there's no issue. It's fine. Okay? If I use this as my prediction. So if this is my prediction model for the central guys. Okay, these guys. Now, what happens if the dashed line is actually the bottom one? Okay, that means that I'll never classify the second class, because if it's the bottom one, then always either the first class is the one which is leading at that point, or it could be the third class which is leading at that point. So at points where I'm supposed to predict class 2, I'm predicting class 1 or 3. So the second class got masked. Okay, that's what I want to illustrate here. Now the thing is, you can't really detect class masking in a general problem. Maybe for 1-2 dimensions you can kind of plot everything and see whether things are getting masked. But in higher dimensions, it's hard to understand whether your class is getting masked or there are some issues like this. So those are the two issues, okay, with doing classification with regression. And there's actually a 2-dimensional example in the notes. So try to intuit that 2-dimensional example as a homework. Okay. Actually, I mean, the 2-dimensional example also, they reduce it to 1 dimension to understand what's going on. So this is kind of good enough to illustrate the point. So, any questions? No questions? Okay, so now we're going to talk about linear discriminant analysis. Okay, so the discriminant, we just said discriminant functions. So linear discriminant analysis, the functions are linear. Okay, linear in X. Okay? It turns out that the functions are linear in X, so that's why it's called linear discriminant analysis. Discriminant functions were those I just said. The beta hat in the regression case, it was just beta hat times transpose X. Okay, for each class. Those are the discriminant functions. So what is LDA? So LDA is basically the use of Bayes rule with some assumption about the following object. So remember, we always have to have like a probability of, I mean, we don't always have to have, but this is a good idea to think about, which is the joint distribution between the variables, input variables, and the output variable, right? So from this point of view, we know the probability of class being equal to, let's say, one class given x is equal to some x is equal to, okay, by the definition of conditional probability, actually by definition of conditional probability, and then also I'll use Bayes rule, so two substitutions. So is equal to probability of x is equal to x given g is equal to k. Okay, this is not true. So there's a term missing, which is the probability of x is equal to x, right? Oh, there's something else missing. Probability of g is equal to k. Okay. So this is just 2 times substitution of conditional probability, and this is called Bayes rule. Okay, in this context. So this is the inspiration behind LDA. Okay. So what does LDA do? it says, okay, so if it's LD as a model, so the model has to have parameters, and this is how I will describe the parameters. We'll assume that there's one parameter, I'm going to call it pi k, for each class little k. Okay, there are capital K classes. Let's say always think of 3 classes, let's say, for simplicity. So the 3 numbers, okay? Those are some parameters in my LDA. That's not the full description. I'll say there are 3 numbers. Okay? That parameterize my model. So those are pi k. I'm just going to call it pi k. Pi is not the 3.14 something. It's just a symbol, Greek symbol. Okay. The second, so this is first. The second thing is I'm going to say that p of x is equal to x given g is equal to k. I'm going to assume it to be equal to normal distribution with some mean mu k and a covariance matrix which doesn't depend on k. Okay. So I need to describe the model. I'm describing you parts of the model. First part was the class marginal probabilities. Okay. Those I did not really assume anything. I literally said it's just keep them as some numbers because these have to be some numbers between 0 to 1. So think of these numbers between 0 to 1. Okay. There's no assumption as such going on over here. The key thing is this guy. I'm going to assume that these are called class conditional probabilities of the feature. Okay. So conditional on the class, what is the probability? What is the likelihood model for the feature? It's a Gaussian distribution. Yeah. Yes. Good question. Yeah. Here, good question. Yes. Here if you're going to assume it normal, if it's not numerical, let's say it's categorical, then you have to do something. Even if you do one-hot encoding, it doesn't look like a Gaussian distribution, right? If you just plot it. Yeah. So here we are assuming things are numerical. Yeah. So even if that feature, here it's actually the full feature vector, okay, whatever the p-dimensional vector. So there could be, if you transform your categorical variables, there will be some coordinates which will be 0, 1 type of coordinates. Then they may not actually be normal if you just scatter plot it or something like that, or actually fit a normal. But you can always say that this is the model description. Model may be far away from the reality. Okay. You can still use this even if your features are not exactly normally distributed it may work. Okay. So that's it. So these are the 2 ideas. First idea is actually just saying, instead of writing this whole thing, I'll just write as pi k. So the capital K number of them, 3 of them for 3 class classification. And the second thing is the probability of the feature vector given class 1, class 2, class 3, there are 3 normal distributions. And each distribution will have its own mean vector. This mean vector is p-dimensional, the same dimension as the feature. And all 3 normal distributions will have the same covariance matrix. Okay. So how many parameters do we have? Pi 1, pi 2, pi 3. For example, 3-dimensional problem, mu1, mu2, mu3, which are p-dimensional vectors, and 1 sigma matrix, which is p cross p. Okay, those are the parameters of this model. Okay, let's say, so now let's understand this. If I know this number, okay, if I know pi k, if I know mu k for each k, and if I know sigma, then can I make my classification? Can I classify a new x? Are those numbers sufficient? Is pi k, okay, let me actually specifically say pi 1, pi 2, pi 3, 3 class classification, mu1, mu2, mu3, and sigma. Are they sufficient to make a classification? They are, right? Because what is my most intuitive classifier here? Remember, base classifier was saying if you know the joint distribution, compute these guys. If you know this for each class k, then take the argmax. Right? That's the base classifier. And here, this happens to be equal to some parametric form, normal distribution, and all that. But if I can compute this, okay, then I can do an argmax as well. Same thing, right? I can take an argmax and find my class. Now, when to do that, for each class k, the denominator is the same, so I don't really care about the denominator. Okay. So what I'm saying is, if I told you this exactly, it's a normal distribution. I told you the parameters, right? You can tell me what's the probability of a given x, right? You can just substitute in the normal distribution density function expression. And if I tell you already pi k for the k class, you know exactly what number to multiply with. So you know for each k, what is that conditional probability of g is equal to k given x is equal to x. So just take the R max, right? So you can at least classify, given if you know the parameters, right? Okay. So, how many of you have heard of a naive-Bayes classifier? People who took 572. What is it?
Night phase.
Naive-Bayes, yes. How many of you have not heard of naive-Bayes classifier? Just one. Everybody else has heard of it. Okay. So when would this reduce to a naive-Bayes classifier?
Conditional, when we have a
Independent.
independent. Yeah, or the conditional dependence.
Tell me, so there is a particular variable x, particular variable g. What is conditional independence stuff going on? Yes. Who wants to be brave and tell me precisely what it means?
When each class,
So for each independent vector, the conditional
There's only one x here. There's only one x input feature,
features,
three-dimensional feature.
yeah, for three-dimensional features.
Yeah.
So the conditional, conditional probability will be u of x1, for example, x1.
This guy, you mean?
Yeah.
Okay.
It will be u of x1 given g is equal to k1 and
Yeah.
x2 given k2.
Yeah.
So we are assuming the conditional independence, and
Yeah.
that will be basically product of all those probabilities.
Yeah. Yeah. Good. So naive-Bayes is just assuming this to be a product over j is equal to 1 to p of probability of x I xj, sorry, is equal to little x j given g is equal to k. Okay. So that's the assumption. That's the number 2 for naive-Bayes. Okay. Naive-Bayes is just saying that's my assumption. LDA is saying this is my assumption. You can go with either, but we are not going to talk about naive-Bayes because it's not in the notes. So that was the model. The model just had the 2 points that I said. But given that model, actually, it also gives a linear classifier. Okay, so sorry, linear decision boundary, just like the regression case. Regression was just beta hat transpose x is equal to another beta hat transpose x. So that was just a linear equation, right? So this guy will also give you a linear equation. And why is that? So for that, let's look at the log of the probability of g is equal to, okay, let me just use 1 given x is equal to x divided by probability of g is equal to 2 given x is equal to x. Okay. So let's say there are 3 classes. Let's look at just the first 2 classes. Okay, I'm just asking what is the log probability of g1 given g2. Divided by probability of g2 given the same feature x. Okay. At a given point, I'm just asking what is the ratio of these probabilities. Okay. Of course, these probabilities have to be. This at least the denominator has to be non-zero. Actually, both of them have to be greater than 0. Okay. For simplicity. So this is just called the. This is just a log ratio of. So this is called the posterior, by the way. Okay. In Bayes rule, the left-hand side is called the posterior. This is called the likelihood. Okay. And this is called the prior. It's just names, but we don't need those names. So why am I looking at this quantity is that because let's say I want to think of a decision boundary. I want to say that it's linear. So how would I say that it's linear? What if these two numbers are the same? At that given x, if these two numbers are the same, okay, let's say 0.6, 0.6, then the 0.6 divided by 0.6 is 1, right? Log 1 is 0. Okay, so I want to kind of say that this equal to 0. This left hand side is some function of x, which is like a linear function. Okay, something like c transpose x. C is some coefficient. I mean, we'll get there. I'm just saying that left hand side is supposed to be some linear function of x. Okay, and I am gonna skip deriving that. only because there's a lot of vector notation because I assume p-dimensional Gaussians because the general formulation at least in the notes is sigma is p cross p, right? These are p cross p, p cross 1, p cross 1, p cross 1. And for that, I don't want to bore you with the definition of a Gaussian uh, density function. Okay. By the way, how many of you are comfortable writing p-dimensional Gaussian's density function? Who's not comfortable? Okay, one way or the other. Okay, the density function. I'll just write the density function just to kind of give you some expression. 1 by square root 2 pi. What's the term there? No. In the p-dimensional case, it's the determinant of sigma times e to the power minus 1/2. Yeah, x minus mu transpose sigma inverse x minus mu. Okay. So this is the expression. I mean, you can specialize this to one dimensional case, right? So if it's one dimension, this is like what is the covariance when one dimension? It's variance. Determinant. I mean, if it's a one number, then the determinant is just that number itself, and square root of that, there will be sigma here, and x minus. So sigma inverse will be 1 by sigma square. So 1 by 2 sigma square. Okay. So x minus mu, x minus mu, x minus mu square. So the idea in one dimensions. Okay, so you can always at least see that one dimensional it works in high dimension. If you use this expression, you will see that the left hand side, we just saw what the left hand side. Each term we know exactly what their expressions are in terms of base rule. The right hand side. So we'll see that this is some function of x. Okay. So what is critical here is that this is a quadratic function. Okay, of x. There's a x transpose x going on here. Okay, that's like a quadratic function, just like beta transpose, something beta. We had that time, right? So in fact, beta transpose beta is a quadratic function of beta, by the way. So what happens is this quadratic function, somehow gets cancelled. Why is that? Because we have a common sigma for each class conditional function. And yeah, and I will not write the expression for discriminant function as well. It's just the log of the left hand side of the base rule previously. Okay? In the previous slide, we saw the log of this thing is just there were three terms, right? So if you just use this, I guess this guy in that equation, you'll get this discriminant function. Okay, discriminant function is just the probability of g is equal to 1 given x is equal to x. That in terms of the parameters. Okay, that's what discriminant function will be. And so in the notes. Yeah, this is an example of doing LDA. So what's really happening? So it says a three class example. Okay, three numbers, 1, 2s, and 3s. Okay, and condition on each class: the green class, the the orange class, and the blue class. The features are supposed to be normally distributed. Okay, that's what the assumption was. Condition on the class is normally distributed. How do you represent a normal distribution from a top view? These are two-dimensional features, two-dimensional feature vectors, x1 and x2 only. The top view would be a Gaussian top view, or this is like the covariance matrix visualization is an ellipse. Okay. If two variables, two Gaussians, unit Gaussians, as in now Gaussian with mean 0 and covariance 1, variance 1, if they're independent, then you'll have a circle. Okay. To just visualize like how if you look at the bell curve from the top, if they're not correlated, it'll look like a circle. If they're highly correlated, it'll look like a very elongated ellipse. Okay, because things are correlated. Okay, here that's why here we're assuming some correlation, so that's why the bell curve looks like a ellipse. And the decision boundary is the region where the bell curve, so decision boundary is the region where the log probabilities were equal to 0, right? It's just so basically you can think of three bell curves. You can just say wherever the bell curve is highest, where does it suddenly become higher than the other ones is the boundary. And it turns out it's linear, okay? And that's what I said. I didn't want to mathematically like bore you with writing all these equations. It's not too many equations, a couple of equations, but so this is the decision boundary, okay? So this is the model, and if you solve it on a particular problem, this is the type of decision boundary you get. Okay. So any questions about LDA? No questions, then we'll do a quiz. Because we have a few minutes. So, okay, for that I need to do something.